Okay, we're going to talk about polar and nonpolar. As the slides get queued up, we'll do a quick little review of ionic versus covalent, which will lead us into our polar or nonpolar covalent. So in terms of review, remember with ionic compounds, we have a metal and a nonmetal. In an ionic compound, we're talking about transfer of electrons from the exchange of the oxidation numbers. So remember, the oxidation numbers were the numbers of electrons gained or lost in order to form the octet, which had a total charge of 0 for the compound. So we started with group 1A, 2A, and 3A. We said once they get married, we're going to change that nonmetals ending to IDE. Magnesium chloride is a prime example. Magnesium is in group 2A, which are the alkaline earth elements. So it's Mg plus 2. Chlorine is in the halogen, 7A. It's a -1. We get MgCl2. So this is ionics. When we're following the table, we had left the d orbitals that dip down. We had left those separate. And what we said was they were a little bit more difficult. They are what we call transitional elements. Transitioning or varying oxidation states means that depending upon how much energy you give it and depending upon the nonmetal it's bonding with, its oxidation state can fluctuate. So we looked at some examples of how we could use the nonmetal to calculate that out so that we would put those in Roman numerals. And that's that middle part of the table. We said there would be 2 exceptions, zinc and silver, that we should be familiar with, that we do not use Roman numerals with, because zinc is always +1, or silver is always +1, and zinc is always +2. Then we talked about the polyatomic ions, and those typically end in ate and ite. You have a whole list of them, so those are going to be ones that you would use your chart for in order to name and write the formulas. The way you can identify those is you actually look and you have 3 capital letters. So notice how we have the F from the iron, we have the S from sulfur, and then the O from oxygen. And remember, polyatomics are more than one nonmetal bonded with a charge. So for these, because it's still ionic, because they're bonding with a metal, we still exchange and reduce. We use parentheses if we want more than one of the polyatomics. So now we look at these 2 nonmetals that come together, and these are covalent compounds, and they are going to be sharing their electrons. So in terms of distinctions, we know that we have 2 nonmetals. They're sharing electrons, and this is when we use our prefixes so that we can differentiate these bonds. Now, why do that? Well, because the lab differences and distinctions are going to be different for both. Ionic compounds tend to conduct electricity, have very high melting points, and are soluble in water. Versus covalent compounds do not conduct electricity. They have much lower melting points. They're not soluble in water. They're soluble in the organics. So that leads us, differences are why we have the different naming systems so that people can identify them easily, and then we see they behave very differently. Covalent compounds can also be broken down into 2 categories, 2 subgroups, and that is polar and nonpolar. So we are going to be taking a look at that, and that is going to be the focus. Now, we talked about electronegativities, and it was alluded to in one of the prior videos that you watched. Electronegativity, remember, is the ability of an element to grab or attract electrons. We can take the difference of those values, and those values are found on charts and tables. So you don't memorize those, you just look those up, and you can Google that. And in math class, when we say difference, what we mean is subtract. So we take the difference between the two atoms that we're looking for. So once we subtract, and this is what they referenced in the other video, is we take that difference and we look at it in comparison to the scale. Now, a lot of books will take our 1.67 and they will actually round it to 1.7. So they'll use that as their comparative value. Anything above it is considered ionic. Anything below it is considered covalent. And we have between 0 and 1 is typically nonpolar covalent, and between 1 and 1.67 is typically nonpolar covalent. So I have an example here of two elements, magnesium and oxygen, magnesium oxide. And, you know, we talked about the idea that you would look up these values, 3.37, 1.29, come from tables, and you don't need to memorize these, you just look these up. So we can see here is magnesium, and then here is the oxygen value that we had written on the other side. And so when we take these values and we subtract them, we end up with a 2.08. We say, okay, that in comparison to 1.7 is higher, so we are going to classify it as ionic. Unfortunately, we can't always rely on electronegativity differences. Just like in English class, when we have exceptions to the rules, we also see that in chemistry. Therefore, we have to take a look at the shapes. Now, I'm going to show another video on shapes that's going to show some of the ball and stick molecules that normally we would put together, pieces we would put together, to see these various shapes so that you can at least get the visual of that. So there's lots of shapes. Typically in Chem 1, we're just going to focus on a few of the basics, the linear. Some texts will refer to it as bent or angular. In other texts, there's trigonals, and then there's tetrahedrals. So those are some of the basic shapes. Notice how this one looks like an angle. Notice how this one we can almost see a triangle. And notice how here it's coming out on all four sides for our tetrahedral. You'll see these made, constructed with those ball and sticks in our next video. So how does that help us? Well, nonpolar molecules are considered two atoms with an even charge distribution. We talk about the idea of molecular symmetry and their electronegativity differences being between 0 and 1. So we take something like methane, okay, it's got hydrogen on all four sides. So that is going to be considered nonpolar. That's an even charge distribution. Chlorine or diatomic, Cl2, that is also, it's got chlorine on both sides. Chlorine is the same size. And then you run into cases where carbon, when you're putting the ball and sticks together, what happens is we went from those dot diagrams when we would write out the chlorine with the 7 valence electrons, and we said it was missing one. So then if it is going to join with something easy like hydrogen, we know hydrogen will give it 1. And so here we have our nice octet. And rather than drawing all these octets of electrons, what we do is we just focus on the bond right where the electrons are being shared. So we use a little stick. So this is representing where these electrons are being shared right here. Now, in some cases, like if we look up carbon, we said, oh, carbon was crazy. It has plus or minus 4. And that's why you can actually study organic chemistry. Notice how we have the name here of methane. Well, that's because we have to follow different rules when we have these carbon compounds that are carbon, hydrogen, chains, and they're also the cyclic compounds, etc. We're not going to focus on the names. We're just going to focus on a lot of these in terms of classifying them as polar and non-polar. Right? If we go with carbon, we can see it has 4, it's in that plus or minus 4 bonding sites. And if it was just bonding with 2 hydrogens, it would actually form a triple bond here. But we can see that it's linear and we've got the same thing on both sides. So this is going to make it very non-polar. So then what do our polar molecules look like? That is everything else. Okay, so polar molecules are non-symmetrical molecules with an uneven charge distribution. Typically, the electronegativity difference is between 1 and 1.67, but we also have to look at their shape. Okay, so anything bent, and water is often considered the universal solvent. Polar, because it's bent, we have this uneven charge distribution, and we have electrons that are over here looking to pull on things and attract things towards it. So that's why when you're talking about lakes and ponds, there's all this water surface tension, because you have what's called intra-hydrogen bonding, where if you have another water molecule that's here, it will tend to attract, because of these lone pair of electrons, over to the hydrogens of the other side. And that gives water some of its unique properties. So this bent and the separation of charge, that is going to be considered very polar. Trigonal, the ammonia, that also we can see there's this whole side over here where it's going to be able to pull on things and attract things very differently. Now, some of the shapes that we typically associate with nonpolar, such as tetrahedral and linear, can be polar if you have a size difference between the atoms. Okay, so chlorine, where it is on the periodic table, is way on the other side and further down from hydrogen. It's got more energy levels, so that makes it much larger. Now, unfortunately, we don't draw things like that, but when we draw it like this, we can see how it's kind of lopsided. This side is going to be much heavier and tend to pull on things differently than this side. So size differences, that is also going to account for things being very polar. So then everybody wonders, why is there all this focus on polar and non-polar? Well, because there's a lot of application to this. I mean, we can start out with soaking our dishes. Why do we soak our dishes? Well, it helps to remove the dirt from the dishes. And what do we add to the water? Oftentimes we add soap. So here we have a very polar compound that we've got in there, and then we add a non-polar to it, and then that will kind of attract, like your oils, break up your oils and your greases and things like that. So this has a lot of application when you're washing clothes. In the washer, you actually have a lot of water, and then you also add your soaps and your detergents, so that those are going to attack the different things that are causing your, getting the dirt all over your clothes to make them clean. All right, the other practical application is chromatography, and that has a lot of practical uses in 2 primary fields, and that's forensics and that's the medical field. So we are going to be looking at chromatography and how we can use polar solvents versus non-polar solvents to kind of separate things out. And it would really be mixtures in order to, we can purify and isolate. So what's coming up next? Well, there's going to be another play posit that you're going to see these ball and sticks. I'm going to have you read about chromatography and some of the labs that are done. I'm going to post an activity that you could try at home, okay, where you'll need a coffee filter and a marker. So if you have it and would like to try that, you'll be seeing aspects of this in some of the videos that you're going to be watching. So then there's going to be the play posit on the chromatography lab types. You're going to read a Chem Matters article on aspirin because these are the fields that these particular concepts apply to. When we talk about medications, especially if we go back historically, where did a lot of medications come from? They came from natural products. So plants, and even now they even, test different types of animals and things like that for medical purposes, for medications. So we're interested, like when I say test animals, like sharks, we know don't get cancer. So why is it that they don't get cancer? Is there something different in their blood, etc.? So we try to do analysis on that, and chromatography allows us to figure out all of the compounds that are within blood and various things. So that you'll kind of see in some of your readings. And then the other big field that really puts a lot of application of these particular concepts is forensics. So I'm going to have you watch one of the forensics files, and then you can see how this is one of the aspects of evidence that they'll use in order to solve a crime. So I would say consider maybe next year, if you like, looking at the labs and what the labs look like, taking that course, because we'll be applying these and other topics to solve those cases. All right, best wishes. Thanks for listening. Over and out.